Okay, thanks, Ray. And it was good to hear about all the interesting work that your team has planned for using TensorFlow. And we'll try to answer as much questions as we can regarding TensorFlow. Okay. So the agenda for today is going to be, I'm just going to briefly talk about what Intel's been doing with respect to deep learning, and especially with TensorFlow, and I'm assuming everybody has used some TensorFlow, so I'll just give you a very high-level overview of TensorFlow, followed by some deep discussions on what we have done to optimize TensorFlow for Intel CPUs. And also, I'll spend some time talking about how you can get maximum performance out of the existing TensorFlow optimizations, and then follow up with some brief summary and call to action. So just very high level, what Intel is doing regarding deep learning and AI. And AI is becoming a very important initiative at Intel. So in addition to building platforms that are highly tuned for AI workloads such as the Xeon families, we've also spent a lot of time optimizing our libraries and introducing specific libraries of features specifically designed for machine learning, especially if you're familiar with the Intel Math kernel library. That's been enhanced to include deep learning also. As you probably already know, software, is most important very important in making sure that the software and the frameworks that people use are highly tuned. So we have an elaborate effort within Intel to reach out to the various machine learning frameworks and work with the open source, either the vendor or the open source community, and help optimize these platforms so that they run best on Intel CPUs. Primarily, I've been focused a lot with TensorFlow, so I'm going to spend most of these conversations on TensorFlow. But I want to say that we do have optimization teams that are working with all the other major framework providers like Caffe, MXNet, CNTK, and a few others. We also have an acquisition that Intel made last year. I won't talk a lot about it today, which brings in a lot of special hardware and software related to deep learning. And this is the company called Nirvana that we acquired last year. Again, TensorFlow, as probably most of you know, is a very generic mathematical framework which is mainly designed for deep neural network, deep learning, but also for using specific math for different HPC applications as well. It's very generic enough that you can use it for HPC applications as well as other machine learning frameworks. And the base core system of TensorFlow is basically a set of kernels, and these are they're designed in such a way that it can be very easily extended to add other user operations. And the core system is written in C++ with a nice front-end wrapper in Python. And also
use these flags to achieve the highest level.
Hello? Okay. And also Google has done a pretty good job of building a multi-node support using the open source gRPC protocol. So as I said, the core of TensorFlow is basically a set of is a computational graph where all the nodes represent various computation and the edges represent tensors or n-dimensional arrays along which the data flows. And the essence of whole TensorFlow can be boiled down to executing this computational graph. Okay, as I mentioned, we've been working with Google for little over about a year right now, and basically taking the existing TensorFlow, which was written which wasn't really fully optimized for CPUs, And we've been working with them to release an optimized version of TensorFlow, and which we released early this year. And what we have done is we've used, as I mentioned, we've modified our MKL libraries to add DNN support or deep learning support. So we've enhanced the TensorFlow to use the Intel optimized libraries, such as the Intel MKL. And the MKL, as you know, has been highly tuned for Intel machines. It uses the codes, the multi-codes, very effectively, and it's highly optimized to use some of the SIMD operations like AVX2 as well as AVX512. In addition, we did a lot of work inside TensorFlow to ensure that the layouts are in the right, the data is laid out in the right way, so that we get maximum performance, and to reduce the scatter gathers, which can, operations which can reduce the performance. And in addition, we found a lot of issues with TensorFlow, the standard TensorFlow, that was in terms of memory allocation. We had a lot of buffers being allocated and reallocated. So we made some changes to TensorFlow to make sure we reuse the buffers and to reduce some of the memory bottlenecks. Right. So to use that, I'll show you a little bit more little later on how to build optimized TensorFlow. But it's basically as simple as downloading Intel, downloading the GitHub version of the master from the GitHub master branch, the TensorFlow code, and just configuring and compiling. After we've done this, we've seen some significant improvement in deep learning workloads. For example, in some cases, we've seen about 70 to 80% speed up in various workloads, especially both for training as well as inference. I'm going to show you some examples of what we've seen. Okay, here's kind of our overview of some of the performance gains that we've seen. For example, we use some of the common ConvNet benchmarks, the deep learning benchmarks. I mean, these are AlexNet, GoogleNet, and VGG. So when we started off, you can see that the performance was very low. For example, the baseline training performance in AlexNet was about 33 frames per second. And after optimization, we were able to get some significant performance improvements for up to probably about 15 to 20x improvement in performance on AlexNet. And we've seen similar performance gains on even GoogleNet and VGG. To gain these optimizations, I mean, to get this optimization, all you have to do is nothing but just compiling and letting TensorFlow use MKL. This again, more performance numbers for Xeon Phi, and here when we started off, we had some very poor performance with the baseline TensorFlow for CPUs. For example, the performance for training on AlexNet was really low at around 12 frames per second. And we were able to bring up the performance by 45 times to about 550 frames per second. So significant boost in performance using the Intel optimized version of TensorFlow. Okay, any questions so far regarding what we have done? Hello? Can you hear me?
Yes, we can hear you.
Okay.
Yes.
Yeah. Okay. That said, we've as I said, we've optimized TensorFlow as best as we can, but to get full performance from the framework, the user has to do some work. Specifically, we've identified several areas where you may have to pay attention to get maximum performance. So if you're doing any CNN or deep learning type of workload, the way the data is laid out plays a significant role in performance. So, for example, if we look at this, this is just a simple two-channel image that I've shown here. You can lay this data out in several different ways. The first one, what we call is NCHW, and the second one is the second format is the NHWC. Depending on which format you choose, the performance could be significantly different. For most of our CPU implementations using MKL, we prefer NCHW format. That's because some of these formats help reduce the need to do scatter gather, and also helps us to effectively use vectorization to use the SIMD operations. So one of the things you need to do is pay attention to what format you're using. TensorFlow supports both formats. Each of the operators support NCHW as well as NHWC. So it's a matter of experimenting and picking the right one. As I said, it's probably a good idea to use NCHW, whenever possible. We see the best performance using that. Okay, the second thing that we would have our users pay attention to is the use of threading. TensorFlow has a threading, a little bit rather complicated threading model, and in addition to that, if you're using MKL brings in its own threading model using OpenMP. So what we've seen is that you need to pay attention and use the right settings for the different threads to get best performance. So for example, TensorFlow has two settings. One is the interop parallelism, and the other one is intra-op. So this is on top. What you can see, the timing diagram that I have is how the operators are executing inside TensorFlow. You can see that it's probably can do up to 3 operators in parallel, and this is actually controlled by the interop parallelism. And then within each operator, it uses a different mechanism, a different setting, like intra-op parallelism. And if these operators are accelerated with MKL, then in addition to that, we also have OpenMP related settings like OMP num threads that need to be set appropriately. Again, these values are highly dependent on the model as well as the platform. I'll show you some things of what we have done to improve the performance of certain workloads, and that could be a good example for you to use when you're tuning your code. So again, as I said, it depends. You could have different settings if you're using the Broadwell platform or if you're using Knights Landing, because they have different cores, different number of cores. Okay, here is a chart that we show some of the settings that we use to get best performance on the workload. For example, we've seen that NCHW performs very well on most of the image-related benchmarks. For AlexNet, we set the interop to 1, and this is for Broadwell, and the interop to 44, which matches the number of cores that was around the platform. Again, KMP block time is another Intel OpenMP settings for how much time to wait before the thread goes to sleep. We found that modifying and changing that on some workloads did give us some benefit in performance. And again, if you can, improving the batch size. For example, we've seen that improving the batch size to 2000 on AlexNet gave us the best performance. And here, what happens is you have more work to distribute across the core. You can see that for the Knights Landing, we had slightly different settings. for the same workload, especially in the intra-op. This is a 68-core knife landing machine, and we had to set in one case we had to set the number of intra-ops to 68, and in the other case we had to set it to 136. And in general, we had to also play around with the OMP num threads for the knife landing. So I think you probably once you have your model ready, it's probably going to take some additional work for you to go and tune the models to get the best performance. Any questions so far?
Yeah, would you have any general rules of thumb about how to approach that? What, in terms of what you know about your problem and what part of the parameter space you should explore?
Yes, I have some files later on that I'll go into.
Oh, okay.
Okay.
Yeah,
any other questions?
So perhaps you might cover it later. You set the OMP num threads for Xeon Phi. Did you have to have any settings for the Broadwells as well and Haswells?
I think for Broadwell, the default setting seems to work well. So I think the default setting sets it to the number of CPUs, I think. So the default setting seemed to work well for Broadwell. It's only for Skylake, it was very sensitive to the settings, so we had to actually go and experiment that on Skylake, on Xeon Phi.
And I think the reason being that by default MKL uses all possible threads available for OpenMP.
Yes.
So,
yeah, okay. I think yes, that is right. But what we've seen is that because number of these operators can execute in parallel, if we set it to the default values, we saw a lot of oversubscription, and that led to other performance issues. So that's why, because of the complicated interaction between the TensorFlow threads versus the OpenMP threads that MKL uses, we had the problem. Yeah.
Okay. I have some more follow-up questions on that later.
Okay. So as I said, to build, any other questions? Okay. To build the optimized TensorFlow is, as I said, very straightforward. Just clone it from the GitHub, and when you run configure, you'll be given an option to include include MKL. Just click on that, say yes, and you can also automatically it's going to download the latest Intel MKL release and configure. And after that is just the standard build. While you build, you need to give a special few switches. We've listed those there. Just configure MKL and a specific pound define that gets passed to the compiler. You can also use additional compiler switches. So if you want to use any specific GCC switches that are specific to the platform, you can also use that. What we have done is we've built a specific basic version without any giving architecture switches, and we still found that had pretty good performance on most of the platforms, because MKL we rely a lot on MKL, and MKL is able to do CPU detect and use the right settings for the platform. So at the compiler level, we don't have to do a lot of tuning to get good performance. But you may also want to try that if you can. And then follow that installation and creating a wheel, and installation is almost identical to the standard TensorFlow. No changes there. That's it. It's pretty simple, straightforward to use the Intel optimized version of TensorFlow. Okay, so here I'm going to go through some of what we have seen in terms we had to do to get good performance. So as I said, the idea is to use the cores effectively and to use them, make full use of them. And we briefly discussed how interop and interop can help with that. So I think the suggestion that we have is probably, to start off with a low number, 1 or 2, the default is 0. That means then it lets TensorFlow choose the right option, and many times we find that's not the right option. And then you can probably try different options. So probably starting off with something low, 1 or 2 is the best. Again, intra-op, that's intra-op. Inter-op, it's good to set it to about the number of cores that you have on the system. And then probably either dial it up or down based on what performance you're seeing. I mentioned the default TensorFlow format is NHWC, but using NCHW does give a lot of performance boost in certain cases. So it might be worth looking into converting your model to use NCHW. This may not be a simple task. You probably have to go through every operator and make sure that you pass the flag. As I said, by default, if you don't pass anything, it assumes NHWC. Plus, you have to modify your data layer where you read in the files and where you read the image files, and you may have to make the changes to put them into NCHW. And again, I think we've seen that if the second argument, this again we have to use in certain workloads, having the second argument of matmul, and if that's transposed, we see some improved performance from the optimized TensorFlow. You can experiment with that too. Okay. Again, there are some, as I said, the settings for the Intel MKL. So some of the things that we played around with obviously OMP num threads. Again, this is an example that we use for the CompNet toolnet example. Also, setting KMP block time seems to help in better utilizing the core. Also, we've tried to do the affinity settings, and in this case, we found these settings to have given some better performance in this workload. So even playing with the affinity settings could help. There are a lot of good tools that you can use. We have used, if you're familiar with the Intel vTune, it's a very useful tool to look at how your threading profile is. And we've used that extensively in our optimization. If you've not used that, you could probably try that. The other feature I briefly showed you when I was talking about threads is the TensorFlow timeline feature. So you can enable that by adding a few simple statements to your model file. You can get an entire timeline of how the operators are executing, how many threads are being used, and you can also look to see what your inter-op should be. Is it too high or too low by looking at the timeline feature? It's a very useful feature, and it also tells you how much time is spent in each of those operators. A very good, useful tool for you to use, and you should explore that. Any questions regarding the tuning of the models? Okay. So I'm going to spend a little bit of time talking about distributed multi-node for deep learning, especially on training. The TensorFlow is very flexible. It has several different models for using the distributed framework. But what we've seen, the most common one is the data parallelism, where you have we have one or more parameter servers and a number of workers. Each of the workers can run on a separate node in the cluster. And the parameter server is kind of responsible for applying the gradients and distributing the weights to the different workers. And each worker runs the full model with its own, partitioned data, and they exchange the gradients or the derivatives with the parameter server. And you can have several parameter servers that can work in conjunction. Some of our analysis that we've done, we found that having one parameter server for every four workers seemed to be a good way of getting the best performance. So we've also done some experiments with this, and I'm going to show you some of what the scaling performance that we got using this model.
If there are multiple parameter servers, do they need to talk to each other as well?
Yes. The parameter servers have to talk to each other. Yes, so they can sync up there between themselves. Yep.
So this would look like would have one more level to the, or the parameter server level in that diagram would have multiple ones with some all to all.
Yes.
Oh.
And okay, any questions before I move on to? I can show you some more information on what we've done. Okay, so we've done some scaling studies on using the various workloads. Right now, gRPC is over TCP/IP is the default communication method that Google uses or TensorFlow uses for distributing weights in TensorFlow. We have just got hold of an early implementation of TensorFlow that uses RDMA, and also there have been a recent release of a native MPI based implementation. We are seeing some issues with that, so we're working with Google to see how we can work with them to fix that and to get to be able to get our customers to be able to use that. But it's kind of very early. So most of our performance that we've done is using gRPC and TCP/IP. The good news is that we are seeing some good scaling on several of the workloads. So we have been able to scale up to 16 workers, and in most cases we needed 4 parameter servers for that. So we've seen that what this chart shows is that for one worker we have let's say it's 100% performance, and we've kind of seen what the scale by adding more workers, 4, 8, and 16 workers. So what this means is if this one is almost 95%, so if you look at Inception V3, it's about 95 or 96% for 4 workers. So what this means is that using the multi-node configuration 4 times we get 90% of the performance of, or 95% of the performance of having four workers, running individually. And if you probably increase to about 16, we still get some good performance, maybe around 90% of that. So we've seen some very good, as I said, pretty good scaling even with gRPC, with TCP/IP. And we are also, as I said, working to improve several of the other workloads to make sure they also scale well with in the multi-node system. Any questions on this? Okay, so I have, yep.
Okay, so MPI, you have initial native MPI support. So those MPI communication performs some data all reduce communication?
I'm sorry, I didn't get your question.
Oh, my question is, in machine learning, deep learning, when the training data, periodically, you need to perform some MPI reduce communication? Is that true? Okay.
I think no. As I said, we are very early in the implementation of what we've seen with MPI. We're still investigating to see what the implementation is.
Okay.
From what we've seen is that it's going to be gRPC over MPI. As I said, we've not investigated this. It just came on, just a few months ago, and we've had issues even bringing it up. We're not able to completely investigate the performance. The idea is that we would be working closely with Google to make sure it's fully optimized for MPI.
Okay.
Any other questions? Okay, I think I've probably this is all I had planned for our for this. So in summary, TensorFlow is pretty widely used framework. It's been used within Google, as well as we've seen a lot of our customers adopting and interested in TensorFlow, and we've done significant work with Google to make sure they're fully optimized for Intel platforms. And we've seen that, in addition to just using the default the Intel optimized framework, we probably have some additional work for the developers to do in terms of tuning their model to make sure that you get the best performance out of for the platform. And it's just some a call to just some links. There's a lot of information on what Intel is doing in the AI. You can get that from the Intel website. And there is this presentation that I made. We have a full blog where it has gone to lots of details about the workload and what we have done. There is a blog that my colleague Mustafa wrote, and he also had a webinar on that, so you can get the link from there. In addition to that, Google itself has a very nice guide on performance optimization. Right now, it's got a lot of GPU-related stuff, but they are adding CPU-related information. Especially some of what we talked about today is going to be, we may be available soon on, to Google, as well as it's going to be available. A lot of it's going to be available on Intel's website. Okay, that's all I had for my presentation. And then we can take on questions.
Yeah, thank you, Ramesh. So now we're opening the floor to discussion. I think, Venkat, you had some follow-up?
Yeah, so actually this is a nice call to action, Ramesh, and thanks for presenting this.
Okay.
And so I actually have been, we build TensorFlow from the Git repo directly, and there have been some additions to support AVX 512 in the, as part of the TensorFlow. The current Git repo, the head is still broken in terms of AVX 512 support. I'm guessing work is undergoing to get that to get AVX 512 support built in.
Yes, we did fix it a while ago, but then somebody made some changes and it broke. So we are aware of that, and we are working, and we'll get a fix out soon. Yes, if you're interested in that, we'll definitely get a fix out soon. It's mainly coming from some of the eigen operations that we've seen. Okay. But if you're using mainly deep learning related operators, then you should not see a lot of performance difference whether you use the 512 switch or not, because most of it is hidden under MKL, which is optimized for AVX 512. But if you have a lot of operators that are not optimized, we don't optimize. As I said, we focus a lot on deep learning. So a lot of the other optimizations, other operators, we don't optimize many of them. So if you're relying on those, then yes, you'll see the error, and we'll make this important. We'll make this high priority to get this fixed.
Okay. The other thing that I've seen is that I've compiled TensorFlow with or I've built TensorFlow with using libxsmm, and
Okay.
and I tend to see at least a slight improvement in performance over using MKL, and these are primarily for more the traditional GoogleNet and AlexNet benchmarks.
Okay.
As well.
You mean even for the traditional deep learning ones also? Okay.
That's right.
Okay.
And this is using some of the. This is using a recent, the 1.2 release candidate one, I would say. It just might be that I haven't, tried several settings, and it might be that if I try additional settings, I might actually get the same performance. That's a study that we internally have to do, and we haven't done a parameter space search till now.
Okay.
Should we be seeing a difference, or can you comment on the MKL DNN and MKL? Should we be getting the same kind of performance with these instead of libxsmm?
No, it's handled out of a different group at Intel. I don't know if we've done a lot of performance studies comparing the two. That is something I have to check to see if there's some information on that. Our focus has been mainly using the MKL version. And as you said, we do publish. I think we've listed either in this presentation or in the blog. We've outlined what are the best switches if you want to replicate our optimizations for let's say AlexNet or GoogleNet. We do have that, and we can send them over to you if you want to look at the settings and.
Okay.
I will take this as an item to check on if there's any comparison between the two libraries.
Okay, so that would be helpful. Okay. And I'm sure others will have questions. I have some follow-up questions, but I just wanted to open the floor to others as well.
So I was wondering if someone has previously been using this is kind of related to what Wei brought up earlier, that people who may have been using TensorFlow in a GPU machine and they're moving to Xeon Phi, would you have any general suggestions about changing the tuning parameters when you do that?
I don't know. We have not done a lot of studies on GPU, but I think at least from porting should be very easy. The TensorFlow makes it very easy to switch between GPUs and CPUs. So I think if you can actually specify what device to use each of your operators. So it's just a matter of switching those from a GPU to CPU. So porting should be easy. Regarding the settings, I think they should just follow the settings that we provide in terms of the threading settings and OpenMP settings. And probably you should see, the best performance that way. And I think, just moving from, as I said, moving from GPU to CPU should be pretty easy in terms of changing the model.
Okay, thank you. Wei? Are you still on? I think we may have lost him. Okay. Are there any other questions?
So I have one more follow-up question, Ramesh.
Okay.
So so when we run it on a Cray supercomputer or an Intel Cray supercomputer which is such as Theta, one challenge that we have found is you have the Intel OpenMP runtime affinities, and then you have the ALPS, which is the Cray runtime affinities, and they tend to conflict with each other. So when we run TensorFlow on our systems here, we have to either one is set the KMP affinity to none. So we rely on the default ALPS space affinity, or we have to we have to disable ALPS affinity and then rely on the KMP affinity. So there might be other attendees who may realize that if you try to set both together, there tends to be a conflict, and you have to set either one or the other.
Okay. Yeah, this is. Yeah, we've not tested on. I mean, we've tested mainly on internal machines. We've not tested them on Cray stuff. Arshaf is our expert on Xeon Phi. Arshaf, do you have any experience there?
Actually, I tried still only Xeon Phi on Intel tools like Intel compiler and Intel OpenMP. So normally, yeah, but so far from my experience, I know that we have to probably do one either Intel. If we use Intel tool, then use the like KMP block or KMP affinity. Or if we use the other tool, the Cray tools, then we have to go with the Cray settings. So that's the normally we do, but I haven't actually try on the Cray tools, and but I have access to some machines, so I can try it. I'm planning to try and see what is my experience. But yeah, for one more thing is for MKL. So for if we just set OMP num threads or any affinity, then actually MKL honors that. So we don't need to set. So MKL has its own threading, and we can set exclusively for MKL. So we can, if we set exclusively for MKL, then MKL will use the exclusive affinity. It will override the other affinities or other number of threads. But if we set just only OpenMP num threads and KMP block time and don't set anything for MKL, then MKL actually uses that one. So that I have made sure. But I'm not yeah, but with the normally for Cray tools, it's we use the Cray affinity and Cray threading and all. We don't do any Intel things. Yeah. So I think that's all. But we can try with the Cray. I think we should try since our many people are using it. We should use the Cray tool, and I'll try that and probably let you know.
Yeah. And if we can exchange. Sorry, go ahead.
Go ahead. You were saying something.
It would be good to exchange some notes on various settings of what we learned. Yeah.
Sure. Yeah.
Okay.
I'll take it as my action.
perhaps in a few months or so, this might be good material for another talk, Ashraf, if you might be interested.
Sure. Actually, I used recently. I used both using GNU compiler and the Intel compiler. So I see some performance differences. For example, if I use like Intel compiler and try with ICC and everything with Intel, then I see there is some performance benefit versus if I use the GNU compiler like GCC 4. GCC 6.2 or whatever we use. So I'm a little bit experimenting more and see if we get more tuning there, Intel compiler versus GNU compiler, and then I will also we can share the information.
Yeah,
Yeah, that would be very arguable.
Yeah, we're seeing similar to the AVX 512 problem that you mentioned, that the Intel compiler, when we run it, actually has a lot of errors. So we're going and we have to work on fixing those errors. So Ashraf mentioned once we have it, we'll probably let our customers know at that point.
Yeah, we actually I fixed those errors, but the thing is still the Google Git master Git has those. There are some types that Intel compiler does not recognize, but GCC recognize. I mean GNU compiler. So we have this issue. So I can build myself, but it's not a user has to change by himself. So that's why I'm thinking is probably need to talk either Google to change those types or Intel compiler to honor those types. Either one should work, and then we'll be ready for ICC. I think it will be easy to compile.
And Ashraf, if you want us to test and give you feedback, we would be happy to do that as well.
Okay, yeah, that will be really helpful. Yeah.
So we've been primarily testing with GCC 6.3 because of the ICC issues that we've seen. But if you're seeing performance improvements with ICC and you have a custom build, we would be happy to even try that out and give you feedback with that.
Oh, okay. Yeah, that will be really great. Yeah. So for AlexNet, I see some performance gain. I'm trying with other models and see if we can tune a little bit more. Maybe a little bit more compiler knobs will help because Intel has some little bit custom knobs that GCC does not recognize, but Intel has. So I'm trying those things, and if it matures like in a couple of weeks, we'll let you know.
That would be very helpful. Thank you.
Yeah.
Okay, so I think I just wanted to make sure I capture some of the main items that. So the first one was the AVX 512 support. The second was libxfxm and performance difference between that and MKL, and the CRADE tools and the Intel compiler. So I think the four things that we need to get back to you on that.
Yeah, that would be helpful. And if you have also, I think Wei is off the line, but went offline. But if you have your settings that you use for using gRPC and doing a parameter server tests, I think that would be something that he would be very interested as well.
Okay.